Hello. If you found this video, it's probably embedded inside of a larger web page going over binary, hex, and other number schemes. I wanted to go over a little bit more about positional notation. So what's the deal with positional notation, really? Well, to explain that, I brought with me an abacus. The packaging for the abacus says it's for ages 3 and up. So that's good. So the abacus is a fairly simple device. Each bead represents a single tally, a single mark, as we count. So here, anything touching the right side is going to be counted. Anything on the left side is going to be ignored. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. I've counted to 10. We allow the other rows of beads here to represent different amounts of numbers. So instead of representing a single digit, this bead is going to represent 10 times or all of the beads of the previous row. So I can push this bead here, push these beads there, and I'm back to where I started, or where I ended. I'm at 10 again. 10, 20, 30, 34, 35, 36, 37, 38, 39, 40, and we can represent 40 like that as well. Now, this might bother you. In fact, this abacus bothers me. It bothers me a lot because I don't consider this abacus, which again was for ages 3 and up, to be a base 10 abacus, which is to say, to be in the base system that we use all the time every day. No, I think this is a base 11 abacus because I think that after you have counted to 10, that the action of going minus 10 plus 11 should bring you as a plus 1, right? So you should be moving beads to count and then move beads again, and that's still just another plus 1. As opposed to having here this state representing 10 and this state also representing 10. I don't like that ambiguity. If there's one arrangement of beads, I want that to only be able to represent one number, and it turns out we can do that. I have another abacus. With this abacus, the middle bar is the bar that is, when beads are touching it, you count them. So this column, this section of 4 beads here, each of these represents a single digit. 1, 2, 3, 4. The top bead here would be 5, so plus 5 minus 4, 5, 6, 7, 8, 9. So when all the beads in the first row have been counted, we're at 9, not 10. Plus 10 minus 9, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So for any arrangement of beads, there's only one possible number, and each column can hold up to 10 values. The reason it's so long is so that we can store numbers on this side and on this side, and then keep track of a multiplication process. Let's look briefly at positional notation and decimals. Let's take a number. I'm going to choose the number 1337 for no particular reason. And we are going to look at this in positional notation terms, where each of these symbols, each of these scribbles, these arbitrary arrangements of pen strokes that don't mean anything on their own, we imbue meaning in them. Anyway, each of these number symbols is in a place. So the first place here where this 7 is would be times 10 to the power of 0. This place would be times 10 to the power of 1, or 10, times 10 to the power of 2, or 100, times 10 to the power of 3, or 1,000. And the only thing you need to remember is that raising something to the power of 0 it's 1. It's just 1. So this 7 times 1 is 7, 3 times 10 is 30, 300, and 1,000. Add these all up, and we're back to our original number. But all I did was take a number, break it apart to its different places, and then add them back together. But that's the same process we can do to look at binary or hex numbers. So let's do that. I'm going to use the example of 2a, because that sounds like it should be easy. So a, we're going to do times 16 to the power of 0, 2 times 16 to the power of 1, Any other places, 16 squared, 16 third, so on and so forth. So A, what is A? All I need to do is write out my numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, and then just count. 7, 8, 9, 10, 11, 12, 13, 14, 15, right? So it's 10, 11, 12, 13, 14, 15. Right, we're just continuing continuing our numbers with the beginning of the alphabet. Why not? So A is 10, and we add that to 2. And that one I know, that's 2 times 16 is 32. So this should give us 42. Let's check our math using this converter. Hexadecimal 2A is, in fact, 42. An excellent answer. Hexadecimal and binary share a unique property, and that property is that they are both powers of 2 in their base system. So binary is base 2, and 2 is a power of 2, and 16 is a power of 2 for hexadecimal. It allows us to do something very clever, which is to represent, when we have binary, to display it as hexadecimal. And however much space that the binary might take up, hexadecimal will take up a consistent amount of space as well. Because when they need another digit, that rollover will happen at the same time. So I've drawn some numbers here, 0, 15, 16, 255, and 256, and I've written them out in binary and in hex. So in binary, the value 0, 0 is 0, but the value 1111 is the largest value we can store in 4 bits of information, and that's the largest value we can store in one place of hexadecimal information. So to get to 16, the number 16, not the 16th value, the number 16, we need another, we need a 5th bit here, 5th place, and a 2nd place in hex. The same is true for the much more common 8 bits from 0 to 255, which is from 00 to FF in hexadecimal. Because to get to that one extra spot, again, that's going to add that extra bit, and same to get to the 3 places of hex. So when you have 8-bit numbers, you're often going to see them written down as 2-digit hexadecimal numbers. And that's super convenient, because looking at binary sucks. Looking at hex kind of sucks too, but just way less. So that's good. It's one more thing I want to draw our attention to, and that's HTML color codes. So you've probably seen these, maybe not knowing what they are. If you've ever used any color picker in any graphic design software like Photoshop or Illustrator, or if you've ever looked into the code of a web page, which I recommend you all do. I just realized I said that in a video on a web page. Don't look at this web page. This web page I wrote by hand. This is gross code. So an HTML color code is a way to encode an 8-bit color. So we have a RGB value, or RGB color here, where the first 2 numbers of this code are the red values. The next 2 digits of this code are the green values, and the next 2 digits of this code are the blue values. And these digits are just hexadecimal numbers. So 8C is 140, if I'm remembering my notes. I don't have that memorized. B5 is 181. Now I'm checking my notes, and I'm confident that that is 145. And that's between 0 and 255. So that is the red, green, and blue values that make up some color that happen to be kind of a desaturated greenish color. This color. There it is. So on the webpage, on this toy, you can see what happens as we choose other colors, which are again represented as just different red, green, blue values. That's another topic for another day. But you can see the different hexadecimal representations of each of these values is in order what make up the HTML color code. The hashtag just being, some nomenclature to say this is where the code begins. And that is, for an extra bit of trivia, sometimes called the octathorpe symbol. So octathorpe. There you go. You can have that. You don't need to call it hashtag. You could also call it a pound sign or a number sign. I'm off topic. In conclusion, if you ever find yourself looking at a whole lot of hex numbers on a computer, relax. At least you're not looking at binary. It could be worse. Also, if you happen to be a toy designer and you're designing an abacus, it should have 9 beads going across, not 10.